US. And so what's the problem? Why haven't we done this? I make it sound very straightforward, very easy, and oh, it's so awesome, why don't we do this? And the problem is, well, two problems really. One is cost. Solar cells are ridiculously expensive. What I'm showing here, this is a few years old, but this is just electricity costs coming from a couple of different sources. So for instance, currently commercial and residential electricity costs are about 10 cents per kilowatt hour. If we were to instead replace those with current solar cells, so silicon solar cells, the price roughly triples. So it goes from about 10 cents to about 20 to 30 cents per kilowatt hour. I don't know too many people that are willing to triple their utility bills. Turns out it's just too expensive, and so it ends up just being cost prohibitive. So the question is, why is it cost prohibitive? So what I'm showing in this graph is basically a history of solar cells, condensed into one slide. Yeah, very condensed into one slide. And there are a number of things to get out of this, which is maybe a little bit out of focus. Can I focus this a little bit better? Nope, that's about as good as it gets. So there are a number of technologies. Most of them are actually shown up here. For instance, in blue, all of the blue lines that you see here are based on silicon solar cells. The green lines are other semiconductor materials, for instance, copper indium diselenide, cad telluride, things like that. The purple here are multi-junction solar cells or gallium arsenide solar cells, depending on which symbol it uses, but tend to be high efficiency solar cells. And the orange down here are kind of newer alternative technologies for solar cells. For instance, this one right here with the hollow line or the hollow dots are called dye-sensitized solar cells, which I'll talk about in a little bit. And then the newer ones right here are organic solar cells. So solar cells based on organic molecules, organic semiconductors. And in all of these, you can see, independent of the technology, all of them have their efficiency increasing over time. Every type of solar cell has become more efficient over time. The longer we do research on it, the more efficient it becomes. But recently, the last 10 years or so, people have realized, scientists at least, have realized that efficiency is not the key metric that we need. We can't just care about efficiency, because as we go up in efficiency, we also go up in cost. And so what we really need to worry about is not efficiency, but cost and efficiency. How can we make things either cheaper, but keep the same efficiency, or increase the efficiency without increasing the cost? And so for the longest time, the way to make a better solar cell was to use better materials, but using better materials is more expensive, and so the cost to efficiency ends up staying the same. So what I'm showing here are three things. So you'll see there's a green oval here, kind of a magenta oval here, and a reddish oval here. The majority of solar cells that are current solar cells are in this region here, region 1. These are called first generation solar cells. And so what I'm showing on this graph is cost of the solar cell on the x-axis and efficiency on the y-axis. And all of these in the green, so all the first generation solar cells, we can pick any place in this green curve, and the cost of the electricity that comes from the solar cell remains roughly the same. We can have a more efficient solar cell, but it costs more to do that. We can have a less efficient solar cell. It doesn't cost as much to do that. So the actual cost per kilowatt of electricity remains pretty much constant. So what we really need to do is get out of this green curve and get down to either the magenta curve, which are second generation solar cells, or this red curve, ideally, which are third generation solar cells. This magenta curve here is, which are the second generation solar cells, are some of the newer technologies on the market. So the thin film solar cells that people may have heard of, that are based on different semiconductors other than silicon. And in this case, we can keep the efficiency about the same as silicon, but it costs quite a bit less. Where we would really like to be, though, is this region 3, the third generation solar cells. Unfortunately, no one's been able to figure out how to get there yet. But these solar cells would be cost effective. these are the types of solar cells that, at least in terms of cost per kilowatt hour, can compete with coal and oil and gas. And so how do we get from here to here to here? To understand that, you really need to understand how solar cells work. And so I'm going to now do some science and explain, hopefully, how solar cells work. At least hopefully everyone will understand me. So, how do solar cells work? To understand how solar cells work, first you have to back up a little bit more and understand that light contains energy. And that light energy, which is in the form of photons, covers a broad range of energies. Most of the energy that we're interested in falls in this region right here, the visible region. So the light that we can see or we use for vision coming from the sun. Most of the energy coming from the sun is in the visible. Some of it's in the infrared, some of it's in the ultraviolet, but the vast majority of light coming from the sun is in this region right here. And so we need a way to turn this light energy into some other type of energy, preferably electricity, which is what solar cells do. And so light contains energy. How can we turn that into electricity? It turns out things, objects, matter, can absorb light. And so what I'm showing here for people who have taken quantum mechanics, this is an inside joke, but when something, some piece of material, some matter absorbs light, it can go from a ground state, a low energy state, to a high energy excited state. So I've chosen to represent this with cats because there's something funny called Schrödinger paradox, or Schrödinger's box, where there's a cat that is neither dead or alive in the box. And so this is a funny quantum mechanical joke if you've taken quantum mechanics. But the important thing here is that this transition from ground to excited requires quantum mechanics. We can't understand what's going on without quantum mechanics. And so when scientists look at how things absorb light, they don't look at cats. They actually look at things like this. So what I'm showing here is the band diagram for silicon. It's overly complicated. You don't need to understand what's going on. But kind of what's going on in this picture is on the y-axis here, I have energy. And all of these black lines are essentially energies that electrons in a piece of material can have. And when some light comes in, it can hit an electron and take an electron from a low energy state up to a high energy state. And it turns out in semiconductors, once it's in the high energy state, it becomes mobile. And so that's why semiconductors can become conductive when you shine light on them. In semiconductors, the electricity or the electrons in these lower energy states aren't mobile. They just sit in place. But once they're promoted up into these high energy states, they can move around the electron and conduct electricity. So what happens when a solar cell absorbs light? Solar cells have to be made out of semiconductors. First thing you have to understand, if they're made out of metals, when light shines on a metal, something different happens. So it's only semiconductors that can do this. In addition, you can't just use, for at least traditional solar cells, you can't just use one type of semiconductor. You have to use at least two types of semiconductor. So what I'm showing here is kind of a cross-section of a solar cell, where the blue is one type of semiconductor, for instance, maybe P-type silicon, which just means that it's missing some electrons. And then this pink here would be another type of semiconductor, for instance, maybe N-type silicon, which means it has extra electrons. So here we're missing electrons, here we have extra electrons. And light is going to come in and shine on this two-material semiconductor. When it does that, so light shines in, and when light is absorbed in a semiconductor, it takes one of the electrons and puts it into a higher energy state. When it does that, it leaves behind a hole, or what's called a hole, which is essentially just a positive, or it behaves like a positively charged electron. If the light is absorbed far from this boundary, nothing happens. We create this electron hole. The electron can move around a little bit, but it can't move very far, and then it meets the hole again, and they just go away. However, if the electron and the hole are formed near this junction, something else can happen. Because this electron is now mobile, it can go into the N-type material, like, too fast, like so. And once it's in the N-type material, it's kind of trapped. It's not going to go back and refine that hole. It has to go in this direction. So you can think of this boundary between the pink and the blue as a one-way valve. Once the electrons cross that valve in this direction, they become trapped and they can't go back towards the hole. Alternatively, any holes that are created in the pink area, once they cross the boundary into the blue, are trapped. They can't go back to catch up to that electron. But electrons are negative and holes are positive, and so they want to come back together and meet each other because they're oppositely attracted. So the only way it can go, the electron can go, for instance, in this case, is through this wire. So through the wire that we would have hooked up to some electrical thing that we might want to use our electricity for. And so it'll go through, it'll power something, which I'm just have as labeled as an external load here, but some electrical thing come through, meet up again with its hole, and then they'll go away. So the whole idea of a solar cell requires that there's essentially this one-way valve between the two materials here, where electrons can only go in one direction and holes can only go in the other direction. And so now that we know how solar cells work, let's talk about A, what makes them so expensive, and B, kind of talk a little bit about how we can solve this intermittency problem. So there are two things that we need to address in solar cells. The first of those is new materials or new types of solar cells. And then the second is just cheaper manufacturing. So how we can make them cheaper instead of using cheaper materials. Now the first question really you should hopefully be asking is why we need new materials? What's wrong with silicon? Turns out there are two things that are wrong with silicon. And the biggest thing is that silicon just doesn't absorb light very well. So what I'm showing here on a graph is a probability of something absorbing a photon of light from the sun as a function of how much energy there is in that photon. And so you can see silicon here, and silicon, the curve for silicon, is underneath the curve for gallium arsenide. If you'll remember back to the history of the solar cell slide I showed, the purple slide was higher than the silicon slide, the purple line was higher than the silicon line for all time. That's because gallium arsenide tends to be a more efficient material for solar cells. It also tends to be quite a bit more expensive. But the reason it's more efficient is because it absorbs light. It absorbs a lot more light than silicon. So you can see, hopefully, silicon is beneath gallium arsenide. But it's not just that it's underneath. This is a log scale. So it's not, this is a factor of 2. This is a factor of 10 to 100. So gallium arsenide absorbs light 10 to 100 times more efficiently than silicon. What that means is silicon has to be 10 to 100 times thicker to absorb the same amount of light as gallium arsenide. But if it's thicker, that means most of it's far away from that one-way valve, or that PN junction. So even when it's absorbing light, the light that's absorbed is too far from the junction to actually do anything useful. So what we really need are materials that are much higher than silicon on this curve right here. So that's the first thing we need to do. The second thing, or the second problem with silicon, is that the only way to use silicon, for the most part, in efficient solar cells, is to make it very crystalline. And because because silicon is used a lot in semiconductor industry, for instance, making computer chips, we're very good at making very pure silicon. It turns out we can make silicon purer than anything else on planet Earth. Silicon, at least semiconductor grade silicon, is some of the purest stuff on Earth. Like way more pure than Snapple even. Yeah. So, but the problem with that is it's expensive. It is very expensive to take silicon and make it extremely pure. So we have this trade-off of needing it to be very pure, but it costing a lot of money. Other materials, such as gallium arsenide, for instance, because they absorb light much better, they don't have to be as pure. They also conduct electrons better, and so we don't need them. We don't need that. We don't have to worry about that junction as much because everything that is in the material can travel far enough to get to that junction. Whereas in silicon, because it doesn't conduct electricity very well, we have to get things closer to that junction before the electron-hole pairs will break apart. So those are the two problems with silicon. So what are people doing to address that? Well, there's a lot of research